Hello everyone, welcome to course study on solid mechanics. In today's lecture, we are going to discuss the concept of generalized Hooke's law for three-dimensional body and for two-dimensional body. Now, first of all, we will discuss about what is three-dimensional body and two-dimensional body. In case of three-dimensional body, the body has three dimensions along x, y and z direction respectively, and that should be in Cartesian coordinate system or a rectangular coordinate system. Now from figure you can see that this particular rectangular block has a three dimensions along x, along y and along z direction respectively. So we can consider this body as a three-dimensional body. Whereas in case of two-dimensional body, it has two dimensions only, and the another third dimension is very small as compared to the two dimension. If I consider the example of the plate or slab, the width and length of that particular slab is very large as compared to the thickness of the slab, so it can be considered as a two-dimensional body. Now in today's lecture we are going to discuss the concept of generalized Hooke's law for the three-dimensional body. The concept of generalized Hooke's law means we are going to derive the relation between stress and strain by using Hooke's law for the three-dimensional body. The figure shows a rectangular block which has the side along x direction, along z direction, along y direction. At the same time, sigma x is the value of stress which is acting over the face which is along x direction. Sigma y, it is the value of stress which is acting along y direction, and sigma z, it is the value of stress which is acting along z direction. Now in the same manner we have epsilon x, epsilon y and epsilon z are the normal strain, it is not normal stress, it is normal strain in x, y and z direction. Now we are going to express the stresses in term of strain. To express the stresses in term of strain, we have to superimpose the effect of individual stress. It means that if I consider the strain along x direction, then we have it is equal to sigma x upon E. This value of sigma x upon E, it is due to the value of sigma x which is acting along x direction. Therefore strain along x direction due to the effect of sigma x is given by sigma x upon E. This is by using Hooke's law only. Now if I consider the value of strain along x direction due to the effect of sigma y, we have the value of minus mu into sigma y by E. That is nothing but it is due to the effect of Poisson's ratio. The strain along x direction due to the effect of sigma y is minus mu into sigma y by E, because when I apply the stress along x direction, there will be the increment into its length along x direction, but at the same time there will be the decrement into its lateral dimension. Therefore the strain along x direction due to the sigma y is given by minus mu into sigma y by E. In the same manner, the strain along x direction due to the effect of sigma z is minus mu into sigma z upon E. Now we are going to superimpose all those values of strain to find out the total strain along x direction. Remember that the total strain along x direction is given by epsilon x upon epsilon x. Now I will superimpose all those load. We have the strain along x direction, it is sigma x upon E. We have strain along x direction due to sigma y, it is minus mu sigma y by E. We have strain along x direction due to sigma z, it is minus mu sigma z upon E. After superimposing all those stresses along x, y and z direction, I have the total strain along x direction, which is equal to epsilon x sigma x upon E minus mu. It is common for both the term, therefore we will take it out from the both the term, minus mu into bracket sigma y by E plus sigma z upon E. In the same manner, we have the total strain in y direction also. Again, it is the individual effect of the stresses along x, y, z direction. Total strain along y direction is given by epsilon y is equal to sigma y by E, because this is the effect of sigma y along y direction. This is the effect of sigma x along y direction, and this is the effect of sigma z along y direction. And after superimposing it, I am having the final value of strain in term of stresses, that is epsilon y is equal to sigma y by E minus mu into bracket sigma x upon E plus sigma z upon E. Similarly, we will find out the value of total strain along z direction, which is equal to epsilon z. Epsilon z is equal to sigma z upon E minus mu into bracket sigma x upon E plus sigma y by E. Remember that those are the relation for the expressing strain in term of stresses. This concept we will use to solve a number of numerical based on it. This is the value of strain in term of stresses for the three-dimensional body. Now in the next lecture we are going to derive, in the next slide we are going to derive the relation of strain in term of stresses for the two-dimensional body. Now as it is two-dimensional body, the third dimension is very small as compared to the remaining two dimension. The strain along x direction, again it is due to the effect of sigma x. Due to the effect of sigma x, we have the strain along x direction, which is equal to sigma x upon E. The strain along x direction due to the effect of sigma y is minus mu into sigma y by E. Therefore, if I superimpose all those stresses, I have the final value of strain along x direction, which is equal to epsilon x equal to sigma x upon E minus mu into sigma y by E. Remember that in case of two-dimensional body, we does not have the stress along any third dimension. If I consider x, if I concentrate on xy direction, then I does not have the stress along z direction. If I concentrate on y and z direction, then I does not have stress along x direction. But at the same time, we have the value of strain along x, y and z direction due to the effect of any two stresses. Therefore, the total strain along x direction is given by sigma x upon E minus mu into sigma y by E. Similarly, I have the total strain along y direction, it is equal to sigma y by E minus mu into sigma x upon E. This is the value of strain along y direction due to the effect of x and y stresses. And total strain along z direction is epsilon z is equal to minus mu into sigma x upon E plus sigma y by E. I have not considered any stress along z direction because we have concentrated on two-dimensional body only, and in that we have concentrated on x and y direction. Therefore, the stress along z direction is 0. But as stress along z direction is 0, but we have the strain along z direction. Therefore, the strain along z direction is minus mu into sigma x upon E plus sigma y by E. Here it is, we have completed a concept of generalized Hooke's law. In the next lecture, we will discuss about the relation between modulus of elasticity and the bulk modulus. Thank you.